continuity in general for Math 1451 at Texas Tech University, which is Calculus 1. So in this first video, like I said, we're just going to be talking about continuity in general. And in subsequent videos to this worksheet, we're going to be specifically talking about continuity with piecewise functions. So in this video, we're just going to be breaking down what is continuity and what types of questions could you be asked about continuity. So a function is continuous at a point, x equals c, if there's no interruption in the graph at that point, meaning if the graph isn't broken and there are no holes, jumps, or gaps. So the images that we have here represent three cases in which a function is not continuous at x equals c. So you may have heard this in high school as a function is continuous if you're able to draw the graph without picking up your pencil. And in essence, that still is what continuity tells us. So if we look at this first graph, there's a hole. So if we're trying to trace this graph, I'll do it in this highlighter. We would have to pick up our pen at that point. For the second graph, we have a clear jump where we have to completely pick up our pen and move it down. And then again here, we have to pick up our pen, go down, and then continue down below. So there are these three cases in which we can have a function that's not continuous. So the definition of continuity where you're able to draw the graph without picking up your pencil is great if we know how to graph the function. If we have a function that's more complicated and we don't know how to draw that graph, that kind of trick of using picking up your pencil breaks down. So what we can do is we can translate this graphical approach into an analytic approach, which is basically what calculus has been training us to do. So instead of thinking about, okay, what does the graph look like? We can instead use our knowledge of limits to know when a function is continuous or not. So an equivalent definition of continuity is that a function is continuous at a point if, first of all, the function is defined at that point. So if we look at this first graph, we can see at x equals c, there's no point on the graph for this x value. There's no corresponding y value here. So in this first graph, the function isn't even defined at this point, so there's no way that it can be continuous because we're going to have to pick up our pen to go over that point in drawing the graph. So first off, we need the function to be defined. Remember that two cases in which a function may not be defined is if we're dividing by 0 at that point, or if we're taking the square root of a negative. Those are two cases that are undefined. Second, we need the limit to exist. So the limit as x goes to c of f of x exists. So we can see on this second graph that whenever we're looking at x equals c, if we trace our limit from the left, we get this point up here. And if we trace our limit from the right, we get this point down here. So this middle graph is an example of our limit doesn't exist because there's a different left and right value. So we're going to see this whenever we have those jumps in the graph is whenever the limit's not going to exist because it's a different left and right value. And finally, we need our function to be defined. We need our limit to exist. And remember, we've talked about the three different cases, or you should have by now in your class, talked about the three cases in which a limit doesn't exist are when it's unbounded behavior, oscillating behavior, or in this case, different left and right. And once we know that, we just need to know that this limit exists, and we want to know that it is equal to the function value. So we want the limit value and the function value to be the same. And that's the issue here in our last graph. So this last graph, our limit is here because when we trace from both sides, that's what we get, but our function value is actually down here. So we can see at each of the three graphs, there's some problem, meaning the function isn't defined, the limit doesn't exist, or those two things aren't equal for each of these graphs that kind of translates to something we can tell analytically, right? And when I say analytically, I just mean without looking at the graph and just looking at the equations that we have, meaning looking at f of x, f of c, and the limit. So when any of these conditions fail, the function is no longer continuous. So one thing to point out here is that we don't need all of these conditions to fail. When any one of them fails, we're done. We know that continuity can no longer happen. So this is great. We know kind of an analytic definition of continuity, but practically, which functions are going to be continuous? So luckily for us, many of the functions that we look at in calculus are continuous, like the polynomial functions, the radical functions, which just means square roots and cube roots and things like that, and the trig functions sine and cosine. But other functions are not continuous. So radical functions, which should say rational functions. Let me fix that there. That's going to be corrected on your worksheet. So this is going to be rational functions. So rational functions are just going to be quotients of other functions. So there's a video on rational functions at the same place you found this one if you need a refresher there. So rational functions, which are fractions of functions, and then the trig functions, tangent, cotangent, secant, and cosecant, and also piecewise functions. So in this worksheet, we're going to specifically look at piecewise functions since these tend to be the more difficult continuity questions that we're going to be asked in calculus. So what questions might you be asked? So there are two main types. So the first type of continuity question for a piecewise function is going to be stating values of x at which a function is continuous. Next is going to be solving for a variable a that makes a piecewise function continuous. So these are the two question types. So for these questions, it's important to remember that if the function has different behavior to the left and to the right, that means our limit isn't going to exist. So we're going to make use of the fact here that we know a limit exists if the limit from the left exists, the limit from the right exists, and that those two things are the same. So that's going to be the approach that we're going to take for these continuity of piecewise functions questions. So this is kind of an overview of what we're going to talk about later in this worksheet, what continuity is, how it looks graphically if it fails, but then also how it looks analytically if it fails. So like I said, at the same place you found this video, you can find the videos that go through the two specific examples on the bottom part of this worksheet. But we hope this helps, and good luck.